Hello everybody and welcome back to Physics 425. I'm not going to start with the roadmap today because we're not going to make very much progress along that roadmap. We're still going to be talking about the energetics of helium-3 and helium-4 mixtures. In fact, today's video will probably be a little bit short, and that's okay because we've had some longer ones recently, and so this will be a little bit of a break. Let me remind you of what we were talking about in the previous video. We were thinking about adding a single helium-3 atom to pure liquid helium-3 and a single helium-3 atom to pure liquid helium-4, and we were trying to figure out which of those two situations is more energetically favorable. And what we argued was that because helium-3 has a larger 0-point energy, those atoms have more kinetic energy, they're moving around more, and so they occupy more space. So that means if you add one helium-3 atom to liquid helium-3, the average distance between neighboring atoms becomes relatively large, and therefore the van der Waals force between adjacent particles becomes weak. On the other hand, liquid helium-4, with helium-4 atoms that have less 0-point energy, occupy less space per particle. The liquid's more dense. So that means when you put a helium-3 atom in there, it's on average closer to its neighbors, and in fact it has more neighbors in its vicinity. And so that means the van der Waals force is stronger and the helium-3 atoms more tightly bound to the liquid helium-4. And so it's energetically favorable for the helium-3 atom to be added to pure liquid helium-4. And one of the ways that we characterized this was by calculating the chemical potentials. And so this was the chemical potential for a single helium-3 atom added to liquid helium-3. And that was just related to the latent heat per particle, latent heat of vaporization. And then we had the chemical potential for a single helium-3 atom added to liquid helium-4. And that one we denoted epsilon, and the important point is that epsilon was larger than the latent heat per particle, so that the chemical potentials looked like this along this axis. For adding helium-3 atom to liquid helium-4, the chemical potential was a larger negative number, so the binding energy was higher. Okay, and so the summary was that the large 0-point energy of helium-3 causes helium-3 atom to be more strongly bound in liquid helium-4 than liquid helium-3. So the question we want to ask today is, what happens if we keep adding more helium-3 atoms to liquid helium-4? So I'm going to make a horizontal axis on this plot, and that horizontal axis is going to represent the concentration of helium-3 in liquid helium-4. So this is X, and this is going to be the concentration of helium-3 atoms in liquid helium-4. So X equals 0 is pure liquid helium-4, and then we can add particles of our atoms of helium-3 a little at a time and increase that concentration. Okay, so we'll come back to that plot. So as more helium-3 atoms are added to the liquid helium-4 of, say, some volume V, each of these additional atoms has to go into a higher energy state. So think of the helium-3 atoms being added to some fixed volume, the volume set by however much liquid helium-4 you have, and that's like having a particle in a box. And so we calculated the available quantum states for a particle in a 3D box. And for fermions, we have a bunch of energy states, and we can only have one spin-up particle in the lowest energy state and one spin-down particle in the lowest energy state. When we add the third particle, it has to go up into the next higher energy state. And it's because the helium-3 atoms are fermions that they have to occupy higher and higher energy states as we add more and more particles. And that's going to be an important point. And so this is because of the Pauli exclusion principle. For fermions. So what actually happens is two helium-3 atoms of opposite nuclear spin can occupy the same state. I should have said at most two helium-3 atoms of opposite nuclear spin can occupy the same state. So let's at most. Nope. Okay, and so let me remind you of one of our results for the Fermi energy. The Fermi energy was written as h bar squared over 2m, 3 pi squared n over v to the power 2/3. And so as n increases, this Fermi energy goes up. And so the energy level of the highest occupied state increases as n to the 2/3 power. So because the energy of the helium-3 atoms increases, so this increase of energy manifests itself as kinetic energy. And so now you can imagine as more and more particles are added, the higher energy particles are moving even more vigorously. They're occupying even a larger space, and the van der Waals attraction between neighboring helium-4s becomes even weaker. And so they become even less bound to the liquid helium-4. So because the energy of the helium-3 atoms increases, the binding energy in liquid helium-4 decreases as the particle concentration X increases. Okay. And so if we go back to this plot, this binding energy in liquid helium-3, I mean, that's obviously a constant, right? And so what happens is, because the Fermi energy of the helium-3 is proportional to, say, N over V to the 2/3, what we see is that this binding energy gets weaker and weaker and weaker, and this curve follows the concentration to the 2/3 power. And at some point, there's a crossover where the binding energy in helium-4 becomes less than it is in helium-3. And so there's some important point right here. And so this is proportional to the concentration to the 2/3 power. And that 2/3 power comes about because of the Fermi energy dependence on the N over V. Okay, so once the binding energy in helium-4 becomes equal to the binding energy in helium-3, so in other words, the chemical potentials, and so the chemical potential of helium-3 atoms in liquid helium-4 is dependent on the concentration, and the chemical potential of helium-3 and helium-3 is some constant. Then it switches to becoming adding additional helium-3 atoms would prefer to actually enter pure liquid helium-3 instead of entering the liquid helium-4, where there's already a whole bunch of other helium-3 atoms occupying the low energy states. So once this condition is met, the helium-3 concentration in liquid helium-4 no longer increases, and additional helium-3 atoms are more strongly bound in liquid helium-3. So in the limit that temperature goes to 0, the limiting concentration of helium-3 in these mixtures is 6.6%. Okay, so that means if I had a bucket of liquid helium-4 close to T equals 0, and then I start adding helium-3 atoms one at a time, they will go into that liquid helium-4 perfectly well until we reach a concentration where 6.6% of the helium atoms are the helium-3 isotope. After that, as we continue to add more helium-3 atoms, what they'll do is they'll float on top of that mixture, and they'll make a phase of pure liquid helium-3 that sits on top. Okay, so therefore what we get is the following type of picture. This is the mixture at T equals 0, and so what we would have is down here, maybe we're going to have a layer of liquid helium-4 with 6.6% helium-3. And this liquid is dense because there's lots of helium-4 atoms in there, and helium-4 is a more dense liquid than helium-3. And then on top of that, what we have is a layer of pure liquid helium-3. And then there's a phase boundary between the two. And so there's a phase boundary separating the pure liquid helium-3 on top and the mixture with 6.6% helium-3 in liquid helium-4 below. Just to finish this idea, we could ask ourselves, what if we added helium-4 atoms to a bucket of liquid helium-3 and a bucket of liquid helium-4? Which situation is more energetically favorable? Well, the argument is the same. Just like was the case for helium-3, the helium-4 atoms are more strongly bound to neighboring atoms in liquid helium-4, just for the same reason. Those atoms occupy less space, so they crowd closer together, there's more neighbors, van der Waals force is stronger. Okay. However, what's different is that as we add more and more and more helium-4 atoms, we wouldn't have the same issue with the atoms having to occupy higher and higher energy states like we did for the fermions in liquid helium-3. And that's because the helium-4 atoms are bosons. And so you can have as many bosons as you'd like in the same energy state. And so they all crowd into the lowest energy state. And as we're adding more and more of these atoms, the energy is not increasing. We're not occupying higher energy states. So since helium-4 atoms are bosons, the binding energy doesn't change. Or it doesn't decrease as more 4 helium atoms are added. Okay, good. So that's a pretty good qualitative picture. I want to show you what actually happens. So experimentally, people can measure the so-called phase diagram of mixtures of the two isotopes of helium. Okay, and so what this is going to look like is we're going to have temperature on one axis, and so this is temperature in Kelvin, and then along this axis we're going to have concentration of helium-3. Concentration of helium-3, and so we'll denote that X. And I'm going to try to draw this with an accurate scale if I can. So we'll see how this goes. So it's going to look something like this. So over here is 1. So that's pure helium-3 on this side. And we said over here at T equals 0, we're going to have 6.6%. And so that's over here. I'm going to draw another line over here. Maybe I'm going to extend this arrow up slightly more. And so there's another line that comes down, something like this. Okay, so here is what we're going to call a normal fluid of some kind of mixture of helium-3 and helium-4. Below this line, and this is going to be called the lambda line, this is superfluid. Helium-3 and helium-4. Okay, so what I want to imagine doing is, let's see if I can build a scale onto this. So around here is 0.75. 0.5 is around here, 0.5. And I guess we have about a quarter. Okay, so the scale's probably not perfect, but maybe I'll move my 0.5 over just a little bit to try to make the scale look a little bit better. So 0.5 is around here. Okay, so what I want to imagine doing is, let's say we start with a mixture up here. And so this corresponds to, let me take a pink line here. And so this is at about 0.4. So we're going to start with 40% helium-3 in helium-4. And I'll also draw a temperature scale. And so over here is about 2 Kelvin. And then here's around 1 Kelvin. That corresponds roughly to where the little peak of this dome is. 2 Kelvin is going to be our starting temperature. And I'm going to put a couple other temperatures on here. I'll put half a Kelvin over here. And then 3/4 of a Kelvin is right around here. Okay, so I think this will work well. Okay, so we start over here with a mixture that's 40% helium-3, and that mixture is at 2 Kelvin. Okay, so we imagine, we'll come back to this figure several times. So imagine a mixture of helium-3 and helium-4 with a concentration of 40% helium-3, and it's cooled from 2 Kelvin to some very low temperature, close to 0 Kelvin. So we're going to kind of imagine this process. So the first step is, when the temperature is equal to 2 Kelvin, the mixture is homogeneous and behaves as a normal fluid. So remember this argument about the 0 point energy of helium-3 being bigger than the 0 point energy of helium-4 is really only relevant at very low temperatures. And so if we're at some elevated temperature, in this case 2 Kelvin, then we're not really worrying about this difference in 0 point energy having an effect on this binding energy, and we just have a uniform mixture of fluid. And so we'll represent that as some volume of fluid that is just homogeneous. And so what we have is a homogeneous mixture of 40% helium-3 and helium-4. Well, mixture of 40% helium-3 in helium-4. Okay. So what we're going to do is we're going to cool this down, and let's suppose that we take this down to a temperature of 1.5. So I'm going to add 1.5 Kelvin on here. And we're going to take this and we're going to go down to, where's 1.5? 1.5 is somewhere around here. Okay, so we take our liquid and we start to cool it. So we go from 2 Kelvin to 1.5. And what we do is we cross this T lambda line. And so let's make a couple comments about that too. So we start to cool our mixture. At around 1.5 Kelvin, the helium-4 component of the mixture becomes superfluid. And so remember, we watched a video of pure liquid helium-4 being cooled, and we saw that the boiling suddenly stopped at about 2.2 Kelvin. And so that was the superfluid transition. And so when the concentration X is equal to 0, this transition happens at somewhere around 2.2 Kelvin. When we increase the concentration, that transition temperature gets lower, and for 40% liquid helium, 40% helium-3, the transition's at around 1.5 Kelvin. So we will discuss superfluid helium-4 later in the course. However, among other things, the superfluid helium-4 can flow through fine capillaries without dissipation, and it is a very good conductor of heat. Okay, so what we imagine doing then is we continue cooling, and then maybe we reach a temperature of something like 750 millikelvin. So we cool this and we reach sub-Kelvin temperatures, and then what's going to happen here is we're going to run into this dome. The inside of this dome is known as a forbidden region. And so this is a forbidden region. And so that means we can't have a concentration of just a block of liquid that is 40% helium-3 and 60% helium-4. In fact, what it does is it separates into two phases. And so if we go to something like 3/4 of a Kelvin, we reach a point over here, and then we reach a point that is over here as well. And so in fact, we follow this the line that defines this dome. Okay, and so what happens when we hit this dome? So the mixture separates into two phases. And so this is where the 0 point energy is starting to become important. At the top of the container, we get a small layer which has a high concentration of helium-3. And so if we go look at our picture, at this temperature of 0.75 Kelvin, the concentration is about 80% in this top layer. Okay, and so XC is around 80%. Okay, so C here means the concentrated phase, which is rich in helium-3. Okay, and so below that, we get a dilute phase, which has less helium-3. And so if we go back to our picture, what is the concentration of that dilute phase? You know, maybe it's just a little bit below 0.4, something like that. And so for this temperature, we would say that the concentration of helium-3 in the dilute phase is something that's a little bit less than 0.4. Okay, because we've lost some of the helium-3 to this top layer. And so what we have is our dilute phase, where X dilute is a little bit less than 0.4. And then on top of that, we have our rich phase, our concentrated phase. So concentrated phase, where XC is around 0.8. Okay, so we've begun our phase separation here, and then as we cool further, we follow this dome, and maybe we go to 0.5 Kelvin. And so over here, we're going to follow this dome, and we get to 0.5 Kelvin over here. Okay, well, what's happened at 0.5 Kelvin is that our concentrated phase is somewhere like 90% helium-3 now, and our dilute phase is something like I think it's about 22% helium-3. And so more and more of the helium-3 is leaving the liquid helium-4 and migrating into the concentrated phase. And that's because as we lower this temperature, the quantum effects become more and more important, and we get this effect of the Fermi energy increasing increasing relative to the thermal energy as we lower the temperature more and more. Okay, so at 500 millikelvin, the dilute phase has a concentration of about 22%, and the concentrated phase is around 90%. And if we draw this picture again, it looks the same, except that the concentrated phase on top is growing. It's becoming a larger fraction of the total volume. And so this is dilute phase 22%, and the concentrated phase has grown a little bit, and it has 90% helium-3 in there. Oh, sorry. Somehow that just crashed, and let's see if I can find that. Oh. Okay. I have to rewrite some of this. XC is 90%. So this is 22. And let's see if it'll let me do it this time. Okay, and so we're almost done. The last thing I want to think about is going to really low temperatures. And so let's suppose we could cool this to close to T equals 0. And so when we do that, when we get to T equals 0, we have our dilute phase, which is 6.6% helium-3 and helium-4. And then our concentrated phase is virtually 100% just pure liquid helium-3 sitting on top. So at T equals 0, the dilute phase is about 6.6%, and the concentrated phase is basically pure helium-3. And the size of our pure phase, our concentrated phase, has grown again a little bit. Okay, good. And so that's basically where I'm going to stop. I'm just going to make one final comment that we will see soon that the finite solubility of helium-3 in helium-4 at T equals 0 is very important for cooling by dilution refrigerators. So this quantum effect, which more strongly binds helium-3 atoms in liquid helium-4 at T equals 0, is going to be critical. The finite solubility means that we have this 6.6% even at the lowest possible temperatures. Okay, thank you very much, and we will chat again soon.